Thank you so much for being here and for sharing your knowledge. And please help me welcome Marcos Cruz.
Thank you, Areti, for the introduction. Can we turn off the lights? Is it possible? It's obviously very special to give this presentation here. I gave, I think, one 2 or 3 years ago, I think. And I was comparing my slides and wanted, first of all, to make sure that I was not talking about the same stuff. And I was glad to feel that, in fact, the majority of slides were not the same slides. So I thought, something happened actually in the meantime. And that's always a sort of positive thing when you return to the same place. The topic that I'm going to talk about really not only excites me profoundly, but I really do believe that has extreme importance. And I'm saying this because I think in one's own career, you go through ups and downs and moments where you sort of doubt of what your contribution is to others. And Areti, you were mentioning the work that I do with Marjan, as Marcos and Marjan, where we did lots of projects and we did research. I finished my PhD. I have been teaching now for over 16 years. And somehow you get to this point where you're sort of reconsidering, what are you doing that might affect others? Is it worth doing it? Is it worth spending this time in what you're doing? And there is a mix of you feeling passion for it with a feeling that others might take this and do something with it. And I have to say, I'm in this sort of beautiful moment where I think I found this currently. And I will show you why and how this is materializing. First of all, I found it with my colleague Richard Beckett, BiotA Lab. So that's in itself a very important moment because we really felt there was a need to create something that has a format and allows this biotechnological studies with architecture to be done with some funding, with PhD students, with master students, and be integrated into something that becomes a bit more institutionalized, because otherwise it's sort of always one running on his own, trying to do everything, but when it gets really to get funding and convince even the world of construction that what you're doing is meaningful, you need something behind you. So BiotA is becoming really a big platform where we are not only doing research, but teaching and looking into the application of stuff. I add this here because when last year I introduced my group here, I called it Sea Biome. And this was is for the group here. This year there were no presentations, so I didn't have the opportunity to talk about it. But clearly for me, one of the differences is that at the IaaC, I think there is a different manner of doing. I think there is a probably more hybrid, and I like that, hybrid manner of applying, making, and producing work that somehow is profoundly speculative and somehow also profoundly real. And this directness that exists in making is something that has really to do with a level of materiality and material consciousness that I think students develop here, that I think is extremely interesting. So I call it computation, biomaterials, and architecture, because clearly that is the platform in which my students or our students here work. And maybe it needs a bit of time until it becomes something again, more formatted and with a sort of sense of progression. I start with a project that maybe you have seen before, which highlights quite a few topics that I find important. And this was the Algae that Marjan and I designed in 2012 during the London Olympics. This was actually a competition that was launched to universities by the Mayor of London, and he asked teams to propose ideas to create something that were these legacy projects. And what we proposed was this pavilion. We called it the Algae gazebo because a gazebo is this pavilion in the park, which is sort of like a sculpture, but it's more than that. It's something inhabitable. And we spend a lot of time questioning ourselves, what was the ambition? What was the technological innovation with the piece? But also what was the design aesthetic? What was the scale even? And we had a good budget, but it was obviously a limited budget. And one of the things we decided was that we wanted to introduce algae with the help of the UCL Algae team into this piece. So we looked at ways of how these algae tubes were inserted and breeding algae from the context. And it took a long time actually with Richard Beckett to discuss how this algae was not only breeding and growing in these test tubes. We didn't want to have only this sort of murky green stuff. How could it be stabilized so that the algae was in fact growing in a controlled way? And after lots of experiments, Richard found this way, which was to carbon impregnate 3D prints. So there was this idea that the 3D print would be sort of embedded in a solution of carbon, and the algae was then going to grow around this carbon. So you can see here when it was inserted, there were these scaffolds on which the algae was growing in a controlled way, at least for the first few weeks. And you can see that on the right-hand side image, that the algae was growing and growing, but it was getting the nutrition from the medium, but it was also controlled within the medium. It was not allowed to circulate. So the progression of growth was very slow in it. So this was an interesting, in a way, discussion we were having with Richard and the UCL Algae team, at the same time that we were dealing with the engineers, Bollinger and Grohmann, in Vienna, with the Vienna team, and using Caramba and some other software, where we were trying to calculate how these cortine surfaces could be perforated. And simultaneously, we were dealing with a German manufacturer who was able to do double steel curvature and again perforate, but actually they didn't know how to do this. And the fascinating topic at the time was that we said, well, we want to have this perforation because we want to make the material lighter. And this manufacturer, who are world specialists in doing this double steel curvature and do the work for Anish Kapoor, didn't know how to do it. And fascinatingly about these processes, how quickly you get to a limitation of making. Means that you have your design, but you can't actually turn it into a reality. And it took many months until they managed, through various experiments, to laser cut and actually plasma cut through a machine, but also by hand, and have a very complex process of how these pieces could be actually curved, because it's a cold curvature, it's not hot, so that there is no expansion of the material, and when you put it together, there is no differentiation of size. And all this process was happening at the same time that we were dealing with the algae team. So there was a simultaneous condition of two groups that didn't have anything to do with each other, that were at some point coming together. Clearly, something that this project relates to is a project we proposed for the MAAC in Badajoz many years before, which was to do with this ornamental perforated condition, but at the time, in 2006, we had no idea how to build it. So it took literally 6 years until we found the opportunity to build. And I often show this relationship because I think the power of recycling ideas is huge. We all do it, it's obvious, but I think for a student's audience, not always obvious, because there's often an idea that you do something, and then, particularly in a master's course, and then you sort of get involved in some other activity, and your project is lost. And clearly, I think the obsessions and the convictions you have with your projects is that they will come back. And they will materialize, even if it takes a few years until that happens. So for us, the MAAC project became then this, what we called inverted foliage. The possibility that this actually very light canopy was stretching out and creating a dialogue on various scales with the context and with nature. So you can see, for instance, here one of these cantilevered pieces is actually rather large, and it doesn't deform because the material has the right thickness, is calculated in terms of engineering, but it has the lightness due to the perforation that is necessary for it to sort of float. And Marjan and I were sort of keen on partly the language, partly the limitations of the perforations, partly the idea that, as the manufacturers were saying, we were probably giving new ideas to Anish Kapoor next time he was doing his installations, that the perforation was probably more interesting than just keeping sort of the bubble as a whole. And as I said, this project of the MAAC was really the driver. Now, these projects, as I said, they don't come from nowhere. They come from the accumulation of other projects. And this is just a quick snapshot of designs that Marjan and I have been involved with on various scales. And I have to say, in this moment of my career, in his career, we were questioning ourselves quite often why we haven't built, or why we haven't built more. So surely there's a sort of issue about these ups and downs, but also this search for your contribution, your meaningfulness is what you're doing. And we often look back at these projects, and there is so much research, because we were doing them while we were doing our PhDs. There's so much research, there's so much sort of knowledge embedded with them that we are using them as sort of the ground, the breeding ground for lots of ideas that we still use nowadays. We have published quite a bit in the meantime. These are sort of compendium of books that Marjan has done and I have done. As you can see, sort of the inhabitable flesh of architecture or digital poetics happened literally at the same time. It's both our PhDs, exuberance or neoplasmatic design, ADs. And I show this because after working with a partner for so long, I think one of the benefits of our working relationship has been that he has done his research, I have done mine, and we have kept that quite separately. We aimed at reading each other's books, and I think we have never done it. And we have never done and read each other's PhDs either. And I think I know him inside out, and he knows me inside out, but there is a sort of level and protection of our own world that is important to keep. And I'm sure many of you will have partnerships, and others had partnerships, and this is sort of like a marriage, and it's a complex process and relationship. But clearly the fact that we publish individually is a very liberating feeling. It gives us autonomy and a great strength to come back again. Obviously what happens is that if one of us publishes 3 times more than the other, that would become a problem because it's unbalanced. Hasn't happened yet, but clearly there's sort of a parallel that happens. We have built a tiny bit. This was the book fair in Lisbon, which was a building for this big book fair that happens every year. And this was actually a competition for the Agropolis, which was not built, but was quite an interesting project in terms of a self-sustainable city on a larger scale. What we have done is build many more sort of installations in a student environment, which are experiments. Some of them are really quite old now and look like a piece of archaeology. But the point is that every time that there's a small construction, it's a fantastic opportunity to test quite a few bits. And these constructions are not buildings. They're neither buildings nor they are models or only prototypes. There's something more than a prototype. We call them the NURBSTER series, which was this continuous idea that these small monsters are 3-dimensional constructions with a particular aesthetic, with particular issues of surface and making. Computation obviously played an important role. Student work has been a quintessential part of my profession. And what I like about the IaaC and what I like about the Bartlett, these are very unique schools where student work is not only something that you produce or the students produce and end up putting in a drawer underneath the bed. It's stuff that is exhibited, it's published, it's out there, and probably 95% of schools around the world copy what is produced in these institutions. They're really the beginners of stuff. Do you know, these are the institutions where new ideas really start. And I think we all have this ambition and the pleasure to witness that and to be part of this idea that maybe not each of us does it, but quite a lot of students really produce stuff that is new, is literally new. And because it's exhibited, it's out there, I think the whole mise en scène that you have around exhibiting and disseminating the work, this plays a huge role. It's not just, by the way, I have produced something and there it is. No, it's a much more profound construction. And this was one of these very nice opportunities we had when, after quite a few years of studies into the sacred and the sublime, we had all these objects that were exhibited in the Baroque church of Nicholas Hawksmoor in London. And we designed these, what we call the Bernini folds. I don't get into so much into that conversation, but the whole idea that a material speaks like another was a very important aspect. The idea that there is a sort of language of the material that can be manipulated and computationally controlled meant that the figural conversations of these models had a reflection on the construction itself. And we did this with students, and I passed through sort of models that have been sort of shown endless times, some of them actually rather large models with 3D prints, and others with something much more sort of complex geometries. And this is, I stop on this one because it's rather recent, which I find has such a fantastic, powerful idea. This lady, Emily Yang, was designing a housing tower in Hong Kong and was looking at the cages and realized these cages are not just ugly in between spaces, between the outside and the inside, and really receptacles for lots of stuff and environmental chambers. They have the potential to become something really designed. And the idea that what is seen as one of the sort of evils of construction in the Asian world, which is these cages that have to do with the obsession of defense and the threat of theft and burglaries, can turn into a design opportunity of great potential. I'm hoping this is sort of being taken by her or somebody else and could become actually a really fascinating design for a building. This is a case of a level of intricate ornamentation ingrained in the geometries of a building that has to do with spiritual values, which has preceded something that is more of a contemporary conversation about geometry, which is this agent-based computation, which has made me question what geometry really means. And we architects sort of believe that we are the owners of geometry. This is really our field. Surely mathematicians do as well. But the applied geometry, the geometry that has to do with form and shape, is really our territory. But when the geometry turns into a set of points and point clouds and agents and cells, and the line, the surface, and the volume become actually rather redundant, because these point clouds are active dynamic systems that probably grow or transform, that live in a constellation, in a network, then there is really something profoundly different. And I find this liberating, actually. I find this fantastically interesting, that what I have learned as an architect years ago of, you know, a set of parameters of what geometry means, and then you heard people saying form died or geometry died. Well, Luis has started looking into the design of these porous systems where really the particles create a permeability of the surface where it really dematerializes and creates a completely new set of conditions. And even more recent, this is something that is actually ongoing currently, is to look at these branching animated systems where these self-generative algorithms determine in a more or less controlled way this new understanding of geometry, this new level of porosity, permeability, capillarity, fibrosity that we are embracing. I show you some of the animations because clearly and surely there's a shift from the static into the dynamic. And I was just invited to give a seminar in 2 weeks' time with Peter Cook on drawings at the RIBA. And the other day we met and we just very briefly spoke about what we might do. And I said to Peter, well, I want to talk about the role of the animation. Is that still a drawing? Is it still considered an act of drawing, or what is this considered? And the animation is not only somebody that knows the software, it's clearly somebody who is looking in how the self-generative algorithms are allowing for rather complex geometric structures and systems to have a sense of directionality, intensification modes, levels of attraction and diffusion that create a completely new horizon of possibilities. Here you can see sort of the morphogenetic transformations where a clear biomorphological paradigm is influencing this level of heavy data complexity and multiplicity of points and branches and vectors that this is creating. The special aspect of what you're just seeing is that many of these Houdini studies tend to be very monodirectional or more monothematic, but the fact that there is a hybridity in how actually biologically these things happen, that smaller scale and larger scale superstructure and microstructural systems interfere with each other and create something that is far more complex than only surface driven or one fiber based system or driven system. So the complexity of intertwined logics that at this stage is almost unarchitectural because it's so diffused and almost unspatial is what is fascinating. There's clearly a sort of stepping into a new territory when these things are controlled towards these sort of biomorphic conditions. I move on because I think the paradigm is not only a metaphoric one, it's actually a real one. So the idea that nature and architecture is interfering with each other is probably being integrated, being embedded with each other, meant that, for instance, in this project of the student, she was looking at something that is a slow motion process where the tiles that keep the growth of the plants in a contained manner have a joint system like our own body joints that can gradually transform. So the forces of nature do not disrupt the artifice of the architecture. It allows it gradually to absorb the forces and adjust. So adaptation and adjustment, it's a very important nuance that matters for this hybridity of nature and architecture. The project that I always show, and now I'm sort of showing less and less, and probably in a few years I'll only show one image, is the Steve Pye project from many years ago when he created these monitors, these bio-receptive monitors that were produced in order to allow the bacteria in our air to colonize the surfaces. Again, fascinating how this is taking around 15 years' time until this project is being taken by others and becoming what we are currently calling Bioreceptive. And I will come back to this project and mention some of these aspects because it really has been really quite a new step at the time that somebody looked at responsiveness and interaction not in a mechanical or electronic way, but actually on a biological level. I have done with Richard a website which is the Cindy Bio. It's a forum that we created where we have a whole set of projects that have been really built where this topic of materializing biotechnological world designs where nature is growing directly in the immediacy of buildings is sort of put together. We have organized actually a symposium this year. We are going to do another one. And clearly there's a family of people. And my message also to the students I have here is that this work is potentially really fascinating, is new, and there are not so many people out there that do it. So the network with those who are in the same family is quite fundamental. We were just invited to Biofabricate in New York 2 months ago, and that was an atmosphere of a family with around 200 people sitting in a room coming from everywhere, feeling, my goodness, we have something to share here. We are the pioneers of some completely new stuff here. And everybody with their own sort of experiments is just making a small contribution to something much grander. That's the feeling I have, that one is sort of really pioneering. Now, unless you're sitting here in the audience, and for me, from my perspective, clearly the Steve Pike legacy, which hasn't influenced Alessio directly, but in my perspective is clearly in this line of a sensibility that certain students have to materialize and build small experiments into something larger, into these sort of bigger than prototype conditions. And this desalination plant embedded within a building wall and surface is a fantastic idea. In fact, I know that Alessio is sort of on a much simpler scale trying to build something in Guinea-Bissau, and for me that's an interesting relationship. A student who is doing a master's course but in fact also trying to build something in reality in a country where there's a real need for this. And there is a sort of dialogue between the more speculative and the real. There's a whole integration of latex sort of containers with a whole network of pipes and this condensation of water that happens within these building facades. The other student, Tobias, also from last year, again was looking at this condition where a material that is pretty available, which is seagrass, can be rethought in a completely different way with the help of computational tools, be integrated in a new thinking mode of what these building skins can mean. Now, is it a skin or is it something else? Big question mark. I might come back to that. You can see here from some of these images that clearly the process was not about building only the roofs and the skins in one go. It's a process of continuous investigation from very small tests, material tests, into much more complex points of integration. This leads me to think that the work that I was supervising, maybe in some respects, was not very different from some of the work that with Marjan and with others we were trying not so long time ago at the FRAC, at the Archilab exhibition, where in our algocelanoid wall, again the geometry of the surface, the three-dimensionality of it, and the integration of something growing looked as simple as it is, but actually is hugely complex. And for me, the main complexity comes from this point, and I have to point it out here, that is this transition. It's the transition between where the algae growth in its own containment breeds over and moves over into the roughness of the surface, and I'm using this word quite consciously, the roughness of the surface that can be potentially bioreceptive. Now, when we did this, we were thinking in bioreceptive modes, but we didn't have the material know-how to make it really bioreceptive. What we wanted to do was to use algae and other small species and bring them onto the buildings, and rather than seeing them as a disastrous problem as it has been seen for a long time, like as you can imagine the owners of that house there thinking about their wall, but see it much more sort of like in a rock, where these algae, and then in particular lichens, can grow for hundreds and actually even thousands of years. But there's a problem with this stuff growing, which is that they look ugly. People think they look seriously ugly. When you have this sort of patchy stuff, these stains, I'm not sure whether I call them stained aesthetics or impure aesthetics, but when this stuff is growing and being self-regulated and you can't control it, where do you as a designer step in? What do you do to prepare where this stuff is growing? But when you look at impure aesthetics, you realize that there was a period where we loved it. Romanticism. The Romantics adored stuff growing on their sculptures and buildings. And you look around and they're fully stained, sometimes fully covered with mosses, sometimes only with patches of lichens. Actually, in this case, Sandra Manso the other day, the biologist who is with us now, just found this case really beautiful in Belgium, where the algae is almost entirely only growing on the top part of this garment that this prophet is carrying around. Something called the molecular engineered house, which is this, again, idea that you can pre-program something that will grow into the form of an inhabitable space. And Peter Cook himself, who had none of these ideas, but was playing with his grand project, the Veg House, one of these projects that he's working on since the 1970s, has been looking at the possibility of intertwining something that is growing, evolving, has moisture, has greenery, has smell, and mix that with the appliances that we have in our houses that often are almost the opposite of that. So the sound harbor, or this sort of kitchen world, is actually, when you think, much closer to some of the realities of how a new kitchen design looks like than what you would ever imagine at that time. And we as Marcos and Marjan were working with this condition of embeddedness, where nature is not only coming from the garden, but gradually moving up to the facade of a building and being integrated into the walls. This has happened for a long time. I mean, it's not that sort of one invented buildings with greenery. If you go to Iceland, you have vernacular buildings covered with grass. Not so sure about the lower case here, where grass is growing in a rather more artificial way on top, and I would imagine that one passes in Florida, somewhere next to Miami nowadays, and probably this green grass looks rather brown if it hasn't rained for a long time. But clearly there's an obsession with this, and the obsession goes as far as, for example, in York Cathedral, they had a sort of grand party for some sponsors, and they covered the entire cathedral internally with grass. You can imagine how crazy this paranoia is becoming. It's sort of getting so crazy that sort of, if you Google it online, you get endless bizarre conditions where people are literally covering themselves or computers or cars or anything with growth under this premise that it's green. It's a sort of green architecture. The reality of green architecture is that it looks actually rather more like this. After a long search, I managed to track down Sandra Manso here in Barcelona. Literally here up the road in the UPC engineering department. She is a biologist. She was sort of buried underneath many layers of formalities and departmental bizarre names, she was actually the PhD student who had looked at bioreceptive materials and bioreceptive concrete. And she referred to Gilitz, who was a biologist in Belgium, who in 1995 was the first time a person saying, well, bioreceptivity is one of the great advantages of materials that we can have, that we should explore rather than see it as a problem. Because the conservationists have been fighting it for years. They have been scratching their heads of how can we get rid of bioreceptive conditions on materials. And there was this biologist who said, no, maybe it's the other way around. Maybe we're supposed to look at the advantages of the materials being bioreceptive. And then Sandra cleverly, in the department here of engineering, with Antonio Guado, the engineer, under his supervision, looked at concrete, which is the second most used material on Earth, and clearly the most important construction material. Now, concrete is not at all bioreceptive. Concrete is very unreceptive because it has a far too high pHD level. It doesn't have sufficient porosity, but after 50 to 80 years, it starts becoming very bioreceptive, and that's when we don't like it. That's when we think it's becoming decayed. So Sandra, in our group at the Bartlett, where she's now with us working, have been looking at the small-scale impact on materials, the medium scale on smaller prototypes, and now with our industrial partner, Lange Rog, where we're starting to think of applying them on very large panels. The construction complexities of manufacturing are obvious, but the growth systems are really complex as well. When she was working on it here, she was looking at these tiny small samples, and they did work. There was a real calibration of the porosity of the material, the surface roughness, and the pH level, so that concrete was really capable to grow stuff. But once you turn it into a larger scale, nothing is guaranteed. And here is the principle of the layering of the concrete, of this bioreceptive concrete, and the first panel we started designing, where these different ridges, as you can see here, are the natural irrigation system where water drains down into the points in which it is absorbed into the material. And what is fascinating about this is that it's all about water absorption, water distribution, and water retention. This is sort of the quintessential issue of life. And for bioreceptive architecture and design, this is the most important aspect. So capillary action, absorption and capillary action of materials is the thing that one has to control. But also the pH level of materials. The fact that certain pH levels do not allow the majority of plants to grow. They just reject them. So we're looking at different thicknesses, different points of absorption. How much surface does exist on this concrete exposed to the outside, and how much is not actually exposed? So we're talking about inhibitors and enhancers. Recently we went to Manchester, because this is sort of a process that never stops, because you constantly discover somebody else who's somehow working in the field or in a related field. In Manchester there is a world expert on capillary systems and materials. And from him we learned that the best manner to actually do the bioreceptive concrete is having a fine material and a coarse material. And the fine material within the coarse will bring the water automatically to the fine one. So there's a concentration process through capillary action that will concentrate the water in the areas that you want, which is the fine-grained capillarity. We as designers, with the engineers and the biologists, are looking at these different bioreceptive morphologies and bioreactive ones. So you look at different conditions where the different patterns of irrigation, the different crevices and nooks and places in which water can be brought into the material but also drained along the material is seen in these different stratifications and patterns. And back to Sullivan and back to the logics of ornamentation, our bark, our design bark, is starting to become something more than a randomly occupied surface. It's starting to have a very particular set of criteria that within an aesthetic dimension is creating a new typology of possibilities. And Alan Penn the other day, who's part of our advisory board, was mentioning that when you look at historically at buildings and you look at cornices and parapets and window frames and door frames and all this sort of stuff that in classical buildings was created, it was created to get rid of water. That's what it was mainly for. There was also a celebration around it, there was a stylistic, but actually the main reason was to get rid of water. So the interest that we have currently is to look at a new set of morphological types which are water absorbent, which are the ones that allow the water to be retained, brought into the material where then growth is going to happen later on. We are looking at patterns of fluidity, obviously, and where growth happens and where not. And as I said, we are intrigued by why things do happen in certain things and not in others. Absolutely fascinating. Here, also small cases where we think the application will be the first step in sort of small pavilions where we want to have the bioreceptivity applied. And this leads me to the parallel exploration that we're doing with students in the master's course, where these morphogenetic studies, where the simulations, where the idea of aggregates and light aggregates mixed with concrete, where metabol studies, in order to create this artificial porosity, this permeability, where not only water but also oxygen is able to provide the right conditions for growth to happen not only at the surface but in something that is far more three-dimensional. And I'm consciously saying here three-dimensional because it ties back into some of the explorations of the algoselenoi or my own PhD research into the depth and three-dimensionality and complexity that can exist with what Martin called the 2.5 dimensionality of the surface, something that has a level of depth. So against the idea of the flatness, this layering of different condition is what we're looking at. Here on this side here, you can see the capillary reaction studies with sandstone. Interesting observation that we made was that in Kew Gardens, there's a rock garden, and the rock garden has a set of those who do the robotics here, really how the different paths were allowing the growth to happen in very particular conditions, but also to do with the rainfall of drops, so in a vertical way. And her screens, her bioreceptive screens, ended up being this large screen that was just hanging here. And again, I hope that this will be taken further. And what I actually realized with those students who I had here and quite a few that I had at the Bartlett is that a lot of this work has the potential to be turned into PhD studies and something that is a much longer research. Because as I said, there's a new ground to explore and something to discover here that needs time to be applied in a more real way. This was our table, which probably the first year students this year didn't see, but those who are in the second year have seen, which was sort of the compendium of possible experiments with all the different materials. At a time when we had our final crit, I made a comment that the work was not particularly beautiful because it was in its initial stages, because it was experimental, and that's what experimental work does. It is not necessarily immediately pleasing. but it is stepping into new ground. And I'm using this image actually as my last one because what fascinates me about bioreceptivity is not only that biology and influenced, biostimulated, biomimetic work can change architecture. I think there is much more about about the biointegration, the bioembeddedness. There's a level of proximity in which nature is really getting onto us and hybridizing, becoming one single thing. And in 2010, I was invited to give a TED lecture, a TEDx lecture at UCL, and I called it Architecture's Path Towards Ecology at the time. And I still think that's what is happening with bioreceptive architecture, which is that architecture is not really architecture anymore. It's really an ecology. And in order to control this ecology, you have to understand these different levels of environmental impact, material conditions, manufacturing complexities, design, and its relationship to culture. Now, that's not an easy task, but this is the beautiful task. This is what I think is creating a completely new era and is fantastically interesting for those who are currently working on this work. I'm glad that there was a biologist who created this word, bioreceptive, because it actually managed to make us now explain what we're trying to do. And it took me years, because we actually were thinking about it a long time ago. Steve Pike in the year 2000 was already sort of thinking about bioreceptivity, because he couldn't explain it. It was sort of said in lots of words and big texts and strange sort of other descriptions. We were missing the terminology, but we have it now. And I think this table here that we had here last year, and hopefully there will be a grander and even better one. I'm sorry, Alessio, but your other colleagues, they will do even more, are just part of this contribution of opening up what is bioreceptive architecture. What are these bioreceptive morphologies? And what are the potential roles of materials and design in making this happen? Because in nature it happens, but we don't know how to do it ourselves. So I finished with this image. I like it a lot because it's sort of, I feel proud of it, and I feel proud of what the students achieved, because it's sort of fantastic work. And I hope you understood some of this, and maybe you have some questions, and I'm happy to answer them. Thank you.
Okay. Thank you, Marcos, for this fantastic presentation on bioreceptive morphologies. You've definitely given us food for thought on what a change in perspective or a change in paradigm and how that can become or transform an apparent downfall into a design tool, an opportunity, and the foundation for the development of a project. I'd like to invite anyone who has questions to raise their hand so I can pass you the microphone. Okay.
Hello, first of all, thank you. Can you lose a few words about the software tools that you're using? I heard Houdini somewhere in the game. Yeah. Maybe why would you choose Houdini over any other 3D modeling packages, or what does Houdini do what others don't do? Or maybe I know there's a few approaches to getting those kinds of shapes. If you could give us a little overview, it'd be very nice.
Currently you can use Grasshopper, you can use processing, and you will achieve very similar results. It's just that Houdini has, first of all, a quite user-friendly interface, as Grasshopper has, but it is closer to the logics of biology in the way it's set up. That means that the way in which, when you use and construct the sort of steps to simulate the growth procedures, the way that is done is clearly in line with what happens with cellular aggregates, cellular diffusion, branching systems in a profoundly biological way. So when you see what Descriptive in Germany is doing, and E2, for instance, who was another one who we actually had over in the Bartlett in Finland, and what our students are currently doing, there is a more immediate relationship in terms of the thinking process that happens between biological morphogenetic systems and computation. And for us this is key, because we don't want, when we are working with this and our students are working with this, we don't want to only replicate or mimic. We need to be conceptually thinking in the same manner. So the tools and the software tools in this case that we're using have to be the inhibitor, the provider of this way of thinking that allows you to bridge into a different conceptual mode. Grasshopper has the advantage that it allows more the manufacturing to happen, which Houdini doesn't. But clearly the imagery that is happening with Houdini is much more powerful. The problem is the control of it. There's extreme difficulty in having really a high level of control, because a lot of it is pretty randomized and it's sort of self-driven by the software. So our ambition currently is somehow to allow, and some of the students are managing to do that now, to have a sense of what's happening in these different steps, one after the other, what's the progression and what's the final output. Amazingly difficult to predict between those who use or are in presence of a certain condition and they interact with it. The response is probably more as a sort of feedback condition. The receptive is almost, in biological terms, the precondition that has to happen. Without the receptive, response and interaction cannot happen. So the idea that one is preparing something to create this host, to create the right conditions that in a way incubate to a large extent what is going to happen, is in nature happening all the time, but is incredibly difficult to control. So I actually have difficulties with the word control, because what we are designing, we're not trying to control, we are trying to create a dialogue. And that's why, again, Bioreceptive is quite beautiful, because receptive is quite, it's not overpowering. It has a level of respect for what happens, but also has a level of control. Do you see what I mean? Because I think there is a constant back and forward we have in our research of until where can we go, and we want to impose, a bit of gardening on the wall, or where's the hands-off gardening condition where we say, actually no, it's about preparing this so that something else will happen.